Hi guys, welcome to Earth Science Week 6. This week we're going to dig a little more into plate tectonics and see what plate tectonics has to tell us about what's deep inside the Earth, which hopefully you'll find kind of interesting. I do. For your warm-up, I'd like you to answer this lecture question number 1, which is, what sorts of things do you think happened as a result of this event on December 26, 2004? The Indian plate, which is the plate represented by the seafloor over here, suddenly moved 50 feet underneath the Sumatran plate, or you could say the Sumatran plate moved over the Indian plate in a sudden event the day after Christmas in 2004. This is in Indonesia. So take a little time, pause the video if you have to, and answer that question. I'm not looking for right answers. Just want you guys thinking and writing stuff down as we're going through. Well, what happened as a result was an earthquake, of course, as you might imagine. See, these pressures build up. I told you that, plates are all moving a little bit each year, maybe 2 centimeters a year. But they don't always move relative to each other that much, and sometimes they build up pressure. As part of them move and what's underneath them is pushing them, they build up pressure, and eventually that pressure releases. And in this case, it had stored up, you can imagine, 2 centimeters a year or so is going to be several hundred years of pressure stored up and then released as that plate moved 50 feet. So, of course, an earthquake happened. That's what happens when there's an earthquake. But that also triggered a tsunami, and that is what was most destructive, and in fact, killing nearly 250,000 people in a terrible tragedy, and one that we are learning from in terms of how to provide warning systems for people in those situations. You may recall a movie based on that event starring Naomi Watts and Ewan McGregor. I've never actually seen it. I will point out, here's another sort of look at it, and you can see how the Indian plate would be subducting here under the Sumatran plate, creating volcanic activity, which takes place on Sumatra, like these volcanoes here. And you can also see, it may not be clear, the Sumatran plate is not just land, but it includes actually a lot of seafloor here that's actually elevated. So a lot of the continental plates versus the oceanic plates are granitic, made out of granite, and they actually float much higher on the asthenosphere than the basaltic plates. And so this entire dark blue region here is part of the Sumatran plate, and the light blue is the Indian plate, and they're moving relative to each other. It's kind of a good view of what the under the ocean would look like if you could see that from space. All right, so this week we're going to dig a little more, like I said, into plate tectonics. And specifically, this is the middle school state standards I've summarized here. You don't have to read through them all. But the two we're going to focus on today are describing the structure and composition of Earth's atmosphere. In 8th grade language, that's just describe in details Earth's structure and composition. And then explain and analyze how the processes of Earth's geosphere result in major geological events. In this case, that geological event would be an earthquake. Some others as well, I guess. So again, we're talking about plate tectonics, this theory we've developed just in the last 100 years, about how these plates are moving around. So do you remember from last week how fast the North American plate, where we live, right here, North American plate, is moving towards the Eurasian plate? If you do, or even if you don't, please write down what you think for your lecture question number 2. You can pause the video if you need to. Or, I'm going to tell you right now, it's about 2 centimeters per year. But write down what you thought it was, if you happen to listen this far. So you can see how these plates move around, and you can see how in Africa here would have fit into the South American plate, and kind of this part of Africa would fit here into the Caribbean. And they've been spread apart by this mid-oceanic ridge here in the Atlantic Ocean for a long, long time. to reach the position they're in today. In fact, it might have looked something like this as Pangea split apart into these different continents. And the continents are still moving today. All right, here's another little test for you. This is going to be your third lecture question. Looking at these pictures here, we're going to look at divergent boundaries, convergent boundaries, and transform boundaries. You may remember from last week that divergent boundaries are places where two plates are moving apart. Convergent boundaries are where two plates are converging or moving together. And transform boundaries are places where two plates are moving relative to each other, like side-to-side motion like that. So, you can see here in the mantle where this would take place. And we're going to look first at fault A, where these two plates, the Juan de Fuca plate, which is just this little bit right here, and the Pacific plate, are moving relative to each other. You can see some arrows dictating which way they're moving. You can also see how in the mantle the convection would be causing motion as the heated magma from below rises to the surface and pushes the plates one to the right side and one to the left side. So, lecture question 3, part A is A divergent boundary, a convergent boundary, or a transform boundary? Lecture question 3B is looking at this boundary between the Juan de Fuca plate and the North American plate, which is this whole thing up here. And the Juan de Fuca plate moving in that direction. In fact, you can see the Juan de Fuca plate subducting here underneath the North American plate. So would we call that a divergent boundary, a convergent boundary, or a transform boundary? That's going to be lecture question 3B. And then lecture question 3C, the San Andreas Fault. Over here in California, you can see that we just looked at the Pacific plate, the Juan de Fuca plate and the Pacific plate here, but they actually kind of come together in this area. The Pacific plate kind of, or maybe you could say the Juan de Fuca plate is already subducted underneath the North American plate. And there's a fault along here, and you can see that the relative motion of the Pacific plate in that region versus the North American plate actually seems a little bit counterintuitive to what you might think. But you have to remember all these plates are moving relative to each other. But you can see their motions represented by these two arrows here. So is that a divergent boundary, a convergent boundary, or a transform boundary? That is lecture question 3C. Pause the video to answer those if you need to. Oh. Unnecessary graphics. Well, the interesting thing about earthquakes is that although they are destructive, and although we can now understand where they'll take place, though we don't understand when they'll take place, we can actually learn a lot about what's inside the earth from these earthquakes by keeping track of where the waves are felt from a particular earthquake. So if an earthquake happens, for example, over here, there are going to be S waves and P waves. You could also call those shear waves and pressure waves that are going to emanate from that earthquake. And they're going to be felt at seismic recording stations all around the world. But interestingly, they're felt in very specific ways, which kind of helps tell us about the Earth. So there is a shadow zone between about 103 degrees and 140 degrees, where because these waves can't move through what we perceive to be the outer core, they're not felt. So we noticed, though we didn't know what the inside of the Earth looked like, and we've never dug down more than about 6 miles or something like that into the Earth's crust. We've never dug down or sent anything down there. We don't, there's no data that we have of actual recovering things that we've sent to probe the inside of the Earth. It's only from using other information like these earthquakes. And we found over time that when an earthquake happened on this part of the world, we couldn't feel it over here, though we could feel it very close by. So maybe, someone at 102 degrees would feel the earthquake, but at 104 degrees, suddenly the stations wouldn't be able to feel that earthquake that occurred in that position. And so over time, we realize, all right, well, there's this shadow zone whenever an earthquake seems to happen, and we don't feel, in particular, these S waves in that shadow zone. And actually, the P waves are felt, but they're felt weakly in a way I'll describe in a minute. And so we sort of said, oh, okay, well, that must mean that this mantle here, though it can move and convect, it also must be mostly solid. But maybe this outer core is such, it must be like heavier metals, first of all, and almost pure liquid, because these particular waves don't travel through them in the ways we would expect. And so that's kind of what we've determined. The outer core must be heavy metals, iron and nickel mostly, which make up this outer core. And the inner core would actually be solid in and of itself. But we've kind of determined that from understanding more about these waves. So we can still feel waves over here, though only P waves and not as strongly. If you look at, and I'll mention also the asthenosphere, part of the mantle, so the mantle is described here, and the crust, just to make sure you understand that the asthenosphere makes up part of the mantle as well as the lower layer of the crust. I just wanted to get that word in your head again, so it doesn't confuse you. These words are sometimes kind of used interchangeably, the mantle and the asthenosphere. This is kind of a cool graphic of how these P waves in particular can be felt. And you can see there are actually 5 different colors depending on what is felt at these particular areas of the Earth. So if an earthquake happens, in this case, in the top here, you're going to see these red emanations are felt as just these waves that are traveling. They actually speed up as they go through the lower part of the mantle, and then they slow down again as they hit the surface. And they're felt over here as sort of normal P waves. Those waves can bounce a little bit, and that's why you see that some of these, the waves that are, the black lines kind of represent the potential for these P waves to bounce. And so these black lines actually bounce, and they call them double P waves, basically. So they can bounce once and sometimes even twice. And this is sort of the direct wave that's felt, and it only travels through the asthenosphere. But then some things change. These pink waves in particular, they slow down quite a bit more, and they become much weaker usually, because they happen to hit this boundary between the mantle and the outer core at just the right angle that they kind of stay along it for a minute and then are diffracted down into this area here, and those are called, I guess, P differential waves or something like that. And so that's a particular kind of wave we feel that kind of ends up in the shadow zone. So these are much weaker waves, and we can tell that the shadow exists because the wave is really strong when you feel it right here, but just down here in that P differential, the wave is much weaker. And then these PKP and PIKP waves are waves that either travel through the light blue waves that travel through the outer core only, or the green waves that travel through the outer core and the inner core because they're directed towards it enough. And each of these waves have different sort of properties that are discernible. Sometimes they build more gradually than the initial signal would indicate they should, the initial earthquake. Sometimes they're weaker in ways that are predictable. And these are all ways that we've been able to figure out how, and sometimes they'll arrive sooner than you might expect than other waves. So in the inner core, they actually travel faster. I think you can even see it here. The green waves slow down, and then they speed up in the inner core, and then they slow down again when they're in the outer core. So the waves actually travel at different speeds through the Earth as well, which is part of how we've been able to put this model together to know what's inside the Earth. But, Mr. Putnam, why do we care what's inside the Earth? Why does it matter? Well, I don't know. Humans just have a quest to know, right? We just want to know what's going on. But there is a little more to it than that, because then we can begin to understand how our Earth functions. In fact, the outer core provides one of the most important services to our Earth that you could imagine. No rock, no iron or nickel from the outer core ever reaches the surface. We don't ever see it, or we're not able to use it. But it serves a very important function, which is that because it's liquid and can slosh around, it actually creates Earth's magnetic field. And you might think, oh, well, that's neat. I can use my compass and I can tell which way is north because we have a magnetic field and I won't get lost in the woods. Well, there's a little more to it than that, because Earth's magnetic field actually protects us from the solar wind, which are charged particles shooting off from the outer surface of the sun, and protons, electrons, even some ionized atoms, alpha particles, and they arrive at Earth's surface, and they would rip our ozone layer, for example, apart, and they would rip some of our atmosphere away. In fact, we might be a lot more like Mars. Mars doesn't have a liquid outer core, and Mars, therefore, has almost no atmosphere, which makes it really hard to breathe if you're, say, an animal. So this outer core serves a very important function, creating this magnetic field, deflecting the solar wind, which might look something like this if you were thinking about how it was coming and how the magnetic field of the Earth was able to deflect that solar wind. It's also, as you might be aware, what causes the northern lights. When the solar wind is especially strong, in particular cycles of the sun or things like that, you can get the northern and southern lights as these charged particles are interacting with the ionosphere, one of the outer layers of the Earth. So thank goodness for Earth's outer core. All right, finally today, I want to start something that we're going to be doing throughout the rest of the class, which is simply considering Earth's energy resources. And I don't just mean anything on Earth that has energy or makes energy, but I'm more thinking of energy resources that humans use. And I want us to keep track of, kind of using this, we'll come back to this picture again and again, and add to our understanding of how and where and why we use these particular energy resources that we use in the Earth. And so, of course, as we've studied the inner part of the Earth, and we've learned about mantle convection and plate tectonics, we realize that there's a lot of heat in the Earth. And we realized that even before we knew there were plate tectonics at places like Yellowstone National Park and near volcanoes and things like that. And we've taken advantage of that to produce geothermal power. You might be able to read that word down here, geothermal power. In fact, if you can't read it, I'll make it bigger for you right here. So we can derive power from the heat inside the Earth. And that's geothermal, just means Earth heat. Well, where does all this heat come from? Why is it hot inside the Earth? You'd think the Earth has been here for 4.5 billion years. Why would there be heat inside the Earth? Wouldn't it have cooled down by now? Well, interestingly, no, it obviously hasn't. In fact, the inner core of the Earth is about as hot as the surface of the sun, and which is kind of amazing when you think about it. And why is that? Well, part of the reason is that as Earth was formed by a bunch of sort of meteorites and asteroids bombarding each other in the early solar system, there was a lot of heat associated with that, and the heat, the heavier metals sank to the bottom, of course, the nickel and iron in particular, and they remained in sort of molten form and were insulated by the materials on the outside. And basically, for 4 billion years, the Earth has retained that insulation to retain a really high inner temperature. So about half of Earth's internal heat comes from that source, as best we can estimate, from the initial formation of the Earth and its the heat associated with that. So we call that leftover heat. The other half, though, comes from an interesting source. You might not realize this, but inside the Earth all the time, in Earth's crust in particular, there are actually not thermonuclear, but nuclear reactions taking place, nuclear fission in particular, where nuclei like uranium nuclei are decaying into thorium and helium and producing heat, energy, just like a nuclear power plant would be producing energy. And there's a lot of uranium, there's also a lot of thorium actually as well, which is the daughter nucleus of this uranium decay, that also then decays and produces energy. So uranium and thorium are all inside the Earth, and they are decaying radioactively to produce heat. So radioactive decay produces about the other half of Earth's internal heat energy that we can then use by, digging down and either pumping some water down into that hot area to try to boil that water and to create some heat that we then spin a generator with, or by other means of deriving. That's kind of the main one, but we could also use water like from a geyser that's coming up towards the surface and pump that into some system to heat steam or turn a turbine to create electrical power, or just to use passively as heating for a floor or something like that. So the inside of the Earth is actually a great source of energy that we are beginning to tap. In addition, I'll point out that nuclear power comes from this same thing. It comes from the uranium and the thorium that we're able to mine inside of the Earth. I should say now most of it actually comes from uranium, which unfortunately produces a lot of fissile material that is radioactive for thousands of years and that we have to dispose of by basically hiding it in places where it won't hurt us. But if we were to start using thorium reactors, which a lot of people think wouldn't be that much harder, it's just that their thorium cannot be weaponized, so we haven't really done as much research in it because we care more about making, for a long time, nuclear research was all about making sure we had enough nuclear weapons to defend ourselves. But thorium reactors actually would be much cleaner and could produce just as much energy as these other uranium reactors. So that's a look at a couple of resources that we obtain from deep inside the Earth that are relevant here for our energy resources. Over the course of the term, we'll investigate the rest of these energy sources as we study the different aspects of Earth that they are relevant to. Are you guys? Maybe I only had 3 lecture questions. Should I give you one more? I'll give you one more. Your last lecture question is to tell me what was the most interesting thing you learned in the last 10 minutes or however long this video was. And once you've done that and sent me your answers to those 4 lecture questions, then you're good to go.